Hello everyone, my name is Lee J. I'm very happy to introduce my recent work about large-eddy simulation of soil moisture heterogeneity induced secondary circulations with ambient winds. This work is supervised by Stephen Paul and Stephen Kollet. Land surface heterogeneity affects the surface energy distribution and can induce a secondary circulation at a certain scale. And the transport by the secondary circulations can lead to an underestimation of energy fluxes by 10% to 30% as measured by the eddy covariance, and leading to energy balance closure problem. While the existence of the ambient wind could affect the formation of the secondary circulations, but to what extent where the ambient wind speed and the directions where affected the secondary circulations remains to be further explored. To answer those questions, we run several simulations with coupled icon large-eddy simulations with the land surface model. The model domain consists of 96 times 96 times 84 pixels with a size of 50 meters in each direction. The simulation lasts 12 hours with a constant incoming radiation of 700 watt per square meter. The figure on the right side shows the idealized model setting with a flat river corridor mimicked by continued soil moisture distribution. The soil moisture is saturated in the middle of the domain and drying to the edge. To investigate the impact of the ambient winds on the atmosphere, we added the wind from different directions: the closed river wind, the parallel river wind, and mixed wind in between. The ambient wind setting is listed in Table 1. Here we set a reference case with both parallel and closed river wind equals to 0. And we also decompose the atmospheric variables into ensemble average, the mesoscale, and the turbulence part based on the equation below. This figure shows the secondary circulation structures of the mesoscale horizontal wind. The structure persists under the parallel river wind, even at a very high wind speed, for example, 60 meters per second. But the structure is destroyed when the closed river wind, here, larger than 2 meters per second. Before the analysis of the bulk properties, I shall introduce you several scaling parameters used in this work: the vertical velocity scale, the fraction velocity, the oblique flanks. And here, the boundary layer height is determined at the height at which the turbulent heat fluxes have a negative maximum. The figure on the right side shows the essential bulk properties over the period of 1 to 12 hours. The dot dashed black line represents the reference simulation. The positive value of heat fluxes indicated the direction from the ground to the overlying atmosphere. And both sensible land and heat fluxes increases with the increase of the wind speed. We will show the details in the next slide. It seems that the boundary layer height, the oblique flanks, the vertical velocity scale, and the fraction velocities does not affected by the parallel river wind, but only affected by the closed river wind here. This figure shows the cross-section heat flux distributions. It is clear that both sensible heat flux and the latent heat fluxes increased with the increasing wind speed, which is more pronounced for the latent heat flux. We can see combined wind speed and the soil moisture dominate the energy distribution, which is independent of the wind direction. We also decompose the total heat fluxes at the lowest atmosphere layer into the advection, the dispersive fluxes, and the turbulent flux. The gray shadow is the range for the simulation with only parallel river winds. It is clear that when the closed river wind is larger than 2 meters per second, both the advection and the perspective fluxes reduced, where the perspective fluxes almost reduced to 0, turbulent fluxes increased and thus reduced imbalance. This figure shows the vertical profile of variances for the vertical wind, horizontal wind, and potential temperature respectively. The total variances of horizontal wind variances are affected under well-formed secondary circulation conditions. The mesoscale variances of the vertical wind represent the secondary circulation strength, while the ambient wind only slightly affects the profile of potential temperature variance. We try to build the relationship between the secondary circulation strength, which is denoted as the maximum value of the mesoscale vertical wind variance, with some scaling parameters. For example, the Bowen ratio, which is the ratio of the sensibility fluxes to the laminated fluxes. The atmospheric stability, which is the ratio of the boundary layer height to the oblique length, and the recently proposed heterogeneity parameters, which is actually the ratio of the buoyancy force to the initial force. The figure on the right shows that there's no relations between the scaling parameters and the parallel river wind. Any dependencies comes from the cross river wind only. We also found there's a strong positive relationship between the secondary circulations and the Bowen ratio, atmospheric stability, and heterogeneity parameters on the cross river winds. This is the take-home message. First, combined wind speed and soil moisture dominate the energy distribution independent of the wind direction. Secondary circulation structures persist under the parallel river wind independent of the wind speed, but it's destroyed when the cross river wind is stronger than the mesoscale horizontal wind, which is 2 meters per second in our simulation. Last, secondary circulation strength positively correlates with the Bowen ratio, stability parameters, and heterogeneity parameters under the cross river winds. Thanks for your attention.